Hi, how you doing? Let's go into horizontal projectile motion now. Okay, so what we're going to be learning about today is horizontal projectile motion. Horizontal projectile motion. Now, what's a projectile? A projectile is anything that's flying through the air basically, and it has both a horizontal and a vertical component to its motion. Something that's falling straight down would not be a projectile. Something that is fired, like for example a bullet or something like that, some cannonball being fired, a baseball being pitched, a golf ball being hit. These are all projectiles because the only force actually working on them is gravity, and they're moving in two dimensions. So they have an x component and a y component. So let's take a look at something here. Let's say we have a cliff, for example, and let's say we have a cannon here. Here's my cannon, and the cannon is going to fire a cannonball straight horizontal like that. All right, and this is the ground down here. There's my ground. It's supposed to be flat and level. Now, what can we say from this picture here? Well, we see that as the ball leaves the cannon, its velocity here only has a direction in the x direction. Let's say this is my x direction, and of course my y direction is in that direction, upward. So y is up, down, and x is left, right. So as the cannonball leaves the cannon, its initial velocity is only the x velocity. In other words, the cannonball is not angled upward or downward, so it's not initially going up or down, it's just going straight out to the right in the x direction. So this is the initial velocity. We'll call it initial velocity. Now, as you might suspect, what's going to happen is the cannonball is going to follow a parabolic path until it finally hits the ground. And the interesting thing about this projectile motion is that at any point along the trip, this is the cannonball at different points along the trip, the horizontal component to the velocity is going to be exactly the same, and it's going to be v sub x, which is whatever its initial velocity was as it left the cannon. That doesn't change. And the reason it doesn't change is because there's no acceleration in the horizontal direction. There's no force pushing it horizontally to make it go once it leaves the cannon. Gravity does, however, act on it, and gravity starts to pull it down almost immediately after it leaves the cannon. We have the force of gravity acting, and so while there's no initial velocity component right up here where it starts in the y direction, by the time it gets moving along, there's a component to the velocity in the y direction downward, and that component gets larger as the cannonball approaches the ground until just as it hits, it gets bigger and bigger and bigger. All right, so we can find the two components of the velocity, the horizontal component, which is the component in the x direction, and the component in the y direction, or the vertical component to the velocity, at any point in time. So let's do a problem. Let me say, for example, that this is 100 meters high off the ground, from there to there. That's 100 meters up in the air. And let's say the cannonball travels, let's say 300 meters before it hits the ground. there. All right, so what we're going to want to do then is figure out, or try and figure out, what the initial velocity was. How's that for a problem? Now, one of the things is we got to split up the components for our velocity into horizontal components and vertical components, and the two of them are absolutely independent of each other and can be solved independent of each other. So first we're going to look at these two components, the horizontal component and the vertical component. So if I take the vertical first, I'll do the vertical here. Let's go it in yellow. So vertical component. I know my formula from the first or second chapter that my displacement in the y direction, or my vertical displacement, is going to be my initial velocity in my vertical direction times the time plus 1/2 the acceleration in the vertical direction times the time squared. My displacement in the vertical direction is going to be minus 100 meters. Why is it minus 100? Because the ball is going downward 100 meters. The ball is going from this position to there, and it's dropping 100 meters down. So that's why we have the negative there, 100, because it's dropping downward 100 meters. The initial velocity in the y direction, well, here's the initial velocity as it just comes out of the cannon, and there is no motion up or down. It's going straight horizontal. So our initial velocity in the y direction is 0 times t plus 1/2. Now my acceleration in the vertical or y direction is going to be due to gravity, and that's negative 9.8 meters per second squared, and then we have time squared. So this equation is going to become minus 100 is equal to, well, it's 1/2 of 9.8 is 4.9, negative 4.9 t squared. So t squared is going to be negative 100 divided by negative 4.9, well, 4.9, and then t will be the square root of 100 over 4.9, and that'll give us the time in flight. That's what we got from the vertical direction. Now what about the horizontal direction? Let me see if I can make some room here. Well, I shouldn't have done that. Let me try and do that in black fill. Whoop, wrong one. Oh boy, I'm really making a mess. Edit, undo. Let's just erase that. And then see if I could fill it with black. Yeah, good enough. Sorry about that. All right, let's look at the horizontal direction then. Do it in yellow. All right, so horizontal. Horizontal. Delta x is the change or the displacement in the horizontal position. The horizontal position is my x position. And that is going to be equal to my initial velocity in the x direction times time, plus my 1/2 the acceleration in the x direction times time squared. But we know that the velocity in the x direction never changes. Since it never changes, it's got no acceleration, and that 1/2 at squared term is going to drop out. So for horizontal motion, the displacement is simply the initial velocity in the x direction that it started the motion with times the time that it's in motion. We know the horizontal displacement is going to be 300 meters. The initial velocity in the x direction we don't know, but we do know what the time is. The time is going to be this value here, which we're going to calculate and then plug in there. And when we plug that in, we got 300 equals Vx times some time that we already know the answer what the time is, and we can solve for the initial velocity. And we'll do another problem in the next video.